How is it going? So we're going to, I apologize in advance that I'm a little bit around today, so I'll be sitting a little more. And maybe not projecting as much as I normally do. So we're going to continue with solving systems of linear equations. Our whole thing in this course, you've probably covered systems of linear equations somewhere else. Here we're just reviewing how the procedure goes, so we can program it. Okay? So we can go bigger. Whatever it is that you were doing in differential equations or whatever other course is probably limited to a 3x3 or a 4x4 system, so simpler systems. And we actually want to get going some calculation so that we can actually solve larger systems, because a whole lot of engineering and science problems come down to solving linear systems, more than you would think. A lot of times the system is sort of like an end results of a procedure of solving a numerical problem. So it's sort of like something that is kind of buried inside some sort of software that you don't even know about. But pretty much every differential equations, ordinary differential equation, partial differential equation, that is discretized. And there is multiple ways we can discretize them. You could study your entire life just with one type of equation and how to discretize it. All of those end up somehow solving a linear system to find the ultimate solution. Okay? So it's sort of like underlying most of the numerical methods out there. Okay? Even though you kind of wouldn't know, it's often hidden. So we're first, again, going to go through solution procedure, and then move this out of the way so I can see most of the class. There we go. So then we can program it. And so just the idea behind one of those procedures, we're going to go through multiple again, is getting system down to an upper triangular system. So we know if I was given an upper triangular system, here's one example. I have upper triangular means that I have zeros below this diagonal. Okay. So then I'm going to attack that by solving this last equation first. So my x3, this is equivalent to this system, right? So when I have A and B given, then the system that is equivalent to it is AX is equal to B, where X are my unknowns. So if these are my unknowns, 4x3 is equal to 8, 3x2 minus 2x3 is equal to minus 1, and the first equation is here. So I basically start the last equation and keep moving up with the knowledge that I gained. So if I got x3 here, I plug it into my second equation, find x2, then I have both x2 and x3, and I move up to the first equation and find x1. So this is essentially the procedure. We're going to go through an example by hand. Now what Gaussian elimination, and Gauss is the mathematician that came up with it, said, okay, so how do I get to an upper triangular system that seems to be relatively simple to solve, right? If I have a general system, here it is, often you can kind of, to write it all together, since we have to transform both A and B, we can put it in so-called augmented matrix. And then we basically figure out how to eliminate this A21 here. If it's non-zero, I look at the numbers and I basically take some multiple of the first row and add it to this row. And we know that we can always do that, right? So when I have two equations, I can take a linear combination of them and replace one of them with that linear combination. So that's precisely what we're going to do. Because that way, we are changing how system looks like, but we're not changing the solution of the system, right? And then we're going to basically proceed in the same manner and eliminate A31. And after that, I'm going to use the second row to eliminate A32. And since I already have a 0 here and 0 here, we'll be fine. We're not going to mess up anything that we've achieved so far. And then in this 3 by 3 system, I'll be essentially done. I'll be at the upper triangular system. You have possibly gone even further. So in a different way, you can actually go and eliminate this one as well as these two. And then you end up with a diagonal system. That's fine too, but we're here gonna, for the sake of programming, just gonna do the first and second part and program them and move on, okay? So let's actually do some examples, and for that I will go to typing, and hopefully my devices will oblige. So let's do first some examples so we can know how to program it. So my Gaussian elimination sometimes it's also called Gauss elimination, either way works. The first step that we will do is transform system into an upper triangular one. And then use back substitution to solve for x's or for x, assuming it's a vector. So let's do an example. The best is done or understood by an example. Let's say that I have minus 3x1 plus 2x2 minus x3 is equal to minus 1. And then 6x1 minus 6x2 plus 7x3 is equal to minus 7. 3x1 minus 4x2 plus 4x3 is equal to minus 6. So essentially, we're going to first go and multiply first row with something and add to the second row and then replace the second row with that in order to eliminate this 6 over here. Okay? And the way to ease calculation is to not constantly write x1, x2, x3, and so forth. So this is why we're going to work with matrices, right? So we're going to put all of these coefficients into a large matrix. Six minus 6, 7, minus 7, 3, minus 4, 4, minus 6. So I'm kind of just separating with like this dashed line my coefficients b. So this is a, and this is b, and this is ax is equal to b, right? So I'm going to go to row 2 and replace it with something that is going to make that first coefficient 0. What is that something? 2 times row 1, right? Will give me in that first stop 2 times minus 3, which is minus 6, plus 6 is 0. Everybody sees that? So if this is my row 1, row 2, row 3, I can replace with 2 times row 1 plus row 2. That's a linear combination of first and second row. So if I do that, I'm going to get 0. 2 times 2 is 4, minus 6 is minus 2. 2 times minus 1 is minus 2, plus 7 is 5. 2 times minus 1 is minus 2, minus 7 is minus 9. Okay? And then with row 3, what are we going to do with row 3? Just add them up, which is a simple linear combination too, right? So it's basically replaced with row 1 plus row 3. Okay? So when I do that, I'll get the 0, minus 2, 3, and minus 7. Okay. So the way we approach this is we eyeball kind of like what would be nice and what would simplify my calculation, right? So I want numbers to be as nice to me as possible. Okay. I want you to start thinking though, what would you do in a general case, how would you tell computer to do that? Can you come up with or start thinking about the rule? We're going to work through that rule. But basically, these are just some numbers. Computer stores them as A00, A01, A02, A10, A1, right? What is the number that you can always multiply the first row, just whatever that number is, huh? And add to the second? What is the coefficient? Hmm? So basically what I'm actually looking, yes, there's a ratio involved. So basically I'm looking, so this is my A00, and this is my A10, right? And I'm looking for a coefficient times A00 plus A10 to be equal to 0. Yes? So my coefficient is minus A010 divided by A00. And my A00 better not be 0. Yeah? So to computer, you would say, well, this is your coefficient that you're multiplying first row with and adding to the second row. Yeah? So there's always a difference. Like we can always use our intuition and our recognition of numbers and try to kind of cut with a computer has to have a clear recipe. This would give a clear recipe, right? And computer doesn't care if it's dividing nice numbers or not so nice numbers. It's dividing, right? Takes the same time to do both. Okay? So this is a general coefficient you could program. Okay, let's just continue with this problem. So now I want to eliminate this location to get to an upper triangular system, right? And what is the simple replacement that I could do? Basically, row 3 minus row 2, that would work. So if we do that, I'm going to go to the next page. So what do I get when I do that? Now I kind of...
-3 to -1.
So first and second row stay the same, right?
Yes. It was 0, -2.
Ah, right. And then I get 0 and 0 as designed. And you're looking at the paper. Can you tell me what?
-2, 2.
2. Okay. So this is now my upper triangular system. And now I proceed with back substitution. My last equation is actually -2 x3 is equal to 2. So my x3 is right? Then I go into my second row, -2x2 plus 5 times x3, but I know what x3 is. It's -1 is equal to -9. So -2x2 is equal to -4. x2 is 2. And then I can plug both in the first one. So I have that -3x1 is equal to -6, is it?
Yes.
So my solution, x1 is 2. This is the part that we will have to program to be more general too. So say that you have a system that is already an upper triangular system, just like this one. Right? I'm just going to kind of write down here using general. So general numbers would be, you want me to do Python numbers or starting from 0 or indices immediately? Yeah? Okay. So then what we really have is A0, 0, A0, 1, A0, 2, 0, A1, 1, A1, 2, 0, 0, A2, 2, x0, x1, x2. So sorry, I shifted now x's, right? This would be Python. Oops. Is equal to my B0, B1, B2. So I'm trying to kind of figure out what the code would look like. That's all I'm doing here. So my A22x2 is equal to B2, so it seems that my x2 is simply, well, divided. And that's always going to be the case, right? going to be B2 divided by A22. And in more general case of an n by n system, this last row is n minus 1, right? So I'm going to start with the knowledge of my x n minus 1 is b n minus 1 divided by a minus 1 n minus 1. Yes? Strictly speaking, in Python, it's going to be this, right? Yes? So that first one will always be easy. Now what I have afterwards is my A11 x1, and I'm going to immediately say it's B1, and I'm going to immediately say minus A12 x2 because this is the stuff I know, right? So my x1 is more generally b1 minus a12 x2 divided by a11. Yes?
Is the reason why you did like n minus 1 is so it starts at the bottom?
So I started from 0, right? So then my last element of the array is position n minus 1. Assuming that it's n elements. And then my A00, so my first, so this is my x1, right? And my A00x0 is equal to B0 minus A01x1 minus A02x2. So my x0 is this B0 minus A01x1 minus A02x2 divided by A00. Is this easy to program? So if I had only, if I was solving 3 by 3 system, and I always knew that I would solve 3 by 3 system, I would plug in these 3 formulas and solve 3 by 3 system by back substitution. But what if my system is of general size? I need a nice little for loop in there. Yes? So one thing that I always know is that I can start from this last one that I know. And then I have to go with for loop with all the other elements, start n minus 1, n minus 3, all the way down to 0, right? And as I go, it's always, so my I need that I rule, something depending on general I, element I or J or however I want to call it. So I'm always going to have, for xi, I'm going to have b of I and a of I involved. And then there's this sum going on here. Yes? So initially I have only one element in that sum, but then I have 2. And that sum is going over all of the previously computed x's. Yes? So we're going to get to this. I just want you, as you're solving this by hand, I want you to start thinking, well, how would I program this? So that I can do this on a 10,000 by 10,000 system and not by hand. Right? And as usual, this is that painful part, is we have to come up with that rule how to generalize through a for loop. right? In this case, we have known size of the system. It's always going to be a for loop, really. Or it's easily done with for loop. It's not that you cannot do it with while loop, right? So that for loop that has to go over all of the elements, right? So I just wanted you to start thinking about. All right, let's do one more problem by hand. Whoa, hi. So one more example. Say I have a system like this. 2x2 plus 3x3 is equal to 6. 4x1 plus 6x2 plus 7x3 is equal to minus 6. And 2x1 minus 3x2 plus 6x3 is equal to 2. So if I write an augmented matrix for this, it's 0, 2, 3, and 6, 4, 6, 7, minus 6, and 2, minus 3, 6, and 2. And again, the reason why we're using this matrix is simply because we don't want to keep writing x1, x2, x3 as we go, as we are changing this coefficient. Okay, now what? I want to eliminate 4. Is there any number I can multiply 0 with to eliminate 4? Trouble. So one thing that we need to remember is order doesn't matter. Order of equations does not change solution whatsoever. So I can simply flip the positions. 4, 6, 7, minus 6, 0, 2, 3, 6, and 2 minus 3, 0, 2. Okay? Order of equations does not matter. So I can change the order. What I call first equation is arbitrary. Okay? What I call second equation is arbitrary. So I can actually change the order of equations to make my life better. Actually, what I call x1 is arbitrary. What I call x2 is arbitrary. I decide what is x1, what is x2. So I could switch the order of those two. What would that be equivalent to switching in this matrix? If I switch positions of x1 and x2. It's not flipping rows. Columns. We're not going to get there. That's something that I hope you're doing in your differential equations. But yes, you can flip rows. That's called full pivoting. All we're going to do is what I call partial pivoting. So partial pivoting basically switches rows in order to remove 0 from pivot position. This is called pivot position. Actually, all of these diagonal positions are pivot positions. Okay, now I can proceed. I already have a 0 in the second row. Great. Yeah. Let's do this one. What would you want to replace this one with?
R1 minus 2R3.
R1 minus 2R3. That works. Okay. So then I'm going to have 4 minus 2 times 2 is 0. 6 plus 6 is 12. 7 minus 12 is minus 5. And then we have minus 6 minus 4 is minus 10. Okay. Now, this is my pivot position. So I'm going to use that to eliminate 12 right below it. This is what I'm eliminating. So what would be a good idea to, what replacement?
Minus 6 row 2.
So row 2 times 6 minus row 3. Yes?
You're not allowed to use row 1?
No.
No.
What would that do?
You can create 4 or
This 4 would mess up your zeros here. Which is why we have to switch the pivot element to the second row. Because that second row has a 0. Great question. Is there a simpler way? Or what was the question?
Like, so we're trying to develop a pattern, right?
Uh-huh.
So can we do it the same way? Because we did R1 minus 2 R3. Can we do R3 minus 6 R2?
We can. Is everybody okay with that? Yes, that works too. So what I pointed out already, like when you're doing this by hand, you find the pattern. If we were sticking to the pattern, the numbers would get ugly. Computer would be fine with them, but we wouldn't. Okay? So when we are programming, we're going to do the pattern. Here on paper, doesn't matter. Okay? So those are but that's an important distinction to make. If you're programming, you can't just throw any, there has to be a pattern for every I being a row, you have to do the same thing. Okay? Or it has to have the same formula. How are you doing it? So that's where I said, okay, this is where the pattern would go. So now I would just find that coefficient. Coefficient times this position is A11. Has to be equal to 1 below, right? So your coefficient would typically be this minus 12 divided by 2 if you were following a pattern. Okay? Always the 1 below negative divided by the pivot position. Yes? Right. So this is now a 0, or it better be. Minus 5 minus 6 times 3 is minus 23. And then minus 10 minus 36 is minus 46. And now we're doing the back substitution. So my last x3 minus 23, x3 is minus 46. So x3 is equal to 2. 2 times x2 plus 3 times 2 is equal to 6. x2 is equal to 0. And 4x1 plus 0 plus 7 times 2 is 14 is minus 6. Minus 20. So my solution is -5, 0, and 2 as a vector. So this again is called partial pivoting. How would you program that? So here you're supposed to use A00 as a coefficient, and you're supposed to divide by it, right? So basically you would check, hey, is A of 0, 0 larger than 0? If yes, proceed as you'd like. If not, go find the row below that you can exchange with. It could be second row, but maybe second row doesn't have a position that is non-zero, right? So you have to kind of search, and what's typically done is that you typically find the row below with the maximum of these. So you find the maximum in the row below, and that's the row that you switch with. So that's called partial pivoting. Okay. And we have time for one more solution. This is more a problem that is more just telling us how do we think about number of solutions that we have in a system. So this example is not so much to point us how to program, but just to what are the things we have to consider when solving systems. And the task is find all solution possibilities based on coefficient CD for the following system. 2x1 plus x2 is equal to C, and 4x1 plus dx2 is equal to 7. This system is so small that whether we use augmented matrix or not doesn't really matter. Everything goes in a 2x2 system. And really, for considering solutions here, anything goes in this 2x2 system. You don't have to necessarily stick to augmented matrix. But I will anyway. So 2, 1, C. And 4D7 is my matrix. And then I'm going to replace this row with what? Plus or minus? What do you pick? In these cases, you can pick, do you want -2 row 1 plus row 2 or 2 row 1 minus row 2? Anybody cares? No? Okay, then this works. So here we have -4 plus 4 is 0, D minus 2, and 7 minus 2C. So now I actually have to I'm about to solve, and the first thing that I would like to do when solving this is divide by D minus 2. But I have to be careful, because what if that is a 0? So let's consider, so now we are considering all of the options. Assume, option 1, assume d minus 2 is equal to 0, right? So d is equal to 2. Then I actually have a 0, 0 here, and then 7 minus 2c. What if that 7 minus 2c is not a 0? So I have two options. It could be 0. Then I have a row saying 0, 0, 0. That's fine. That's a fine possibility. That's a common possibility. And it basically means that that top row was a multiple of the second row, right? So you just eliminated everything. So if also 1a 7 minus 2c is equal to 0, so c is equal to 7 over 2. Then I have 2, 1c, 0, 0, 0. So the only thing that I have is that 2x1 plus x2 is equal to c, which is 7 over 2. That's my solution. Okay? And solution is an entire line. So infinitely many solutions. On a line. If you want to plot that line, it's a line x2 equals to 7 over 2 minus 2x1. All right. The second possibility here, 1b, is that 7 minus 2c is not a 0. Then I have a 0 equals to 0. Something not 0, right? And that means that there is no solution. Because I have an impossible case. And geometrically, if you remember, those are the parallel lines. Okay? I mean, it's confusing, but it's still a solution just fine. There is no solution. Okay, so once these cases are out of the way, now we assume d minus 2 is not 0. Then basically I can divide by it and basically find my x1 and x2, right? So we can divide. And my x2 is equal to 7 minus 2c divided by d minus 2. And x1 is equal to, well, from the first equation, it's 1 over half c minus 7 minus 2c over d minus 2. You can go find what that is. Okay? So infinite number of solutions, no solutions are just fine. They exist. All right. So next time we're going to actually program Gaussian elimination.
Shoot.